Hi folks, Mr. Ackerman here. Thanks for watching. The topic of today's video is standing waves continued, and we're basically picking up from the last video on standing waves. In that last one we talked about standing waves that were fixed at both ends. So an example would be like a guitar string where both ends are held down and you pluck it and waves go back and forth and they interfere constructively and destructively, and you get those standing wave patterns that we demonstrated in class. Well, today the question is, what if one of the ends is not fixed, but rather is free, or sometimes they say open? And for that matter, what if both ends are open, like you just had a, I don't know, a slinky or a piece of rope and you just gave it a little shake, you sent a vibration along it, what would happen? So we'll look at those, and I'll just get you up to speed in the homework schedule. We're on lesson 5, so we continue with 8.1, although we're talking about one end fixed, one end free. And we jump into section 8.3 as well, where you're going to hear some new terms like acoustical resonance in an air column. And basically what this boils down to is standing waves where both ends are free. And I'm going to explain what that's got to do with acoustics, which of course has something to do with sound. And air column, you might be wondering what that is. You're going to find out. So in addition to watching this video, make sure you complete all the notes from section 8.1 and 8.3 that you'd like to take. Have a look at the sample problems that they do. In class we're going to be working on these two sets of questions for the two sections, and I'm going to do some demos for you that you can't do at home, which will hopefully help make everything clearer. Afterwards you can try some additional questions on your own. Okay, let's get started. As far as standing waves with one open end goes, I know you're probably wondering, well, what would be an application of this? I can't imagine a guitar string that's only held down at one end. A guitar wouldn't work if both ends were not held down. Well, as it turns out, it's not just waves in springs or strings that create standing waves, but even sound waves, like the kind you would get if you were dealing with a clarinet, for example. They also are sound waves. And in a clarinet, as you're going to learn when you do your reading, one end of the clarinet behaves as a fixed end, and that happens to be the mouthpiece or the reed end of the clarinet. And of course, if you played an instrument like this or you saw one back when you used to be in music class, then you know that the player puts his or her fingers on the different keys here and closes them off or opens them up. So any one of these keys or these holes, or perhaps even the end, the bell of the instrument, could be the free end. Now you might be thinking, okay, well, aren't sound waves longitudinal? They are. They're not the transverse waves that we look at when we talk about standing waves most of the time. They don't look like this. They're kind of those compression waves, if you remember reading in your book. Remember, they bunch up. They have compression regions and rarefaction regions and then compressions again. However, we're going to represent these compression, these longitudinal waves, as transverse because they're a little bit easier to visualize in that sense. Okay? Think of a trumpet. A trumpet's a musical instrument, also a wind instrument, but it behaves differently than a clarinet. As you're going to see in your reading, it behaves as if there are two free ends. One is at the mouthpiece, and the other would be perhaps at the bell over here. This is called the bell. And that would be another free end. And so you end up with a situation where the waves don't behave exactly like when we have two fixed ends, as in a guitar string that might be vibrating like this. In fact, you might be wondering what I'm talking about at all. How can this possibly work? Well, here's a video that I found online. It's from the Massachusetts Institute of Technology, MIT, and I'm just going to go over there right now, and we're going to have a look. If you're looking on YouTube, by the way, this is what it looks like. So type in Bell Labs Wave Machine Reflection. Now, I've been loading this for about 20 minutes now, and the internet's awfully slow. So I just downloaded the clip using another program, and I'm going to play it to you in this media player. Here's what the clip looks like. I want you to watch. It's kind of neat. There's this experimenter who is glowing. Now, he didn't drink something radioactive. They're just shining a light on him, and it's glowing because he's wearing white. And along here are a series of, well, basically wooden or metal rods which are free to vibrate up and down, and they sort of pivot on the midpoint here. You're going to see this in a sec. And they're glowing in the dark, so when this experimenter sends a pulse along these poles, you're going to see exactly what it does when it gets to the end, which is not held in place. In other words, it's free. Check it out. There goes the pulse. And when it comes back, you can see it is in the same phase that it was before. So let's go back a little bit here. The pulse was sent as a crest. You're going to see it up here. Here it goes. And it comes back as a crest. In other words, the reflected wave is in the same phase as the incoming wave. That's what happens when a wave reflects at a so-called free end. I'm going to show it to you again. There's actually no sound in this video. There's no narration, so that's why I've muted it. Now what they're going to do is show you what you already know. It's going to hold this end, and what do you think is going to happen? You get a reflection in the opposite phase. A crest becomes a trough. And this is, of course, what we see in class when we do this. It's easy to do reflection at fixed ends. It's not easy to do it at free ends unless you have that piece of equipment. And so that's why I chose to show you this YouTube video. Anyway, now I hope you can believe that when an end is open or free, you can get different standing waves than you can get when the end is fixed, like it is over here with a guitar string, for example. So now let's look at exactly what happens. So I've designed a chart here, which hopefully will help us to figure out what's going on. In the first column here, we're going to look at some of the possibilities for waves that are formed when there's one end free, one end closed. And then in the other column, we're going to look at what happens when both ends are free. So for example, you might have a wave that's been sent down a rope which is fixed at one end, and therefore you know at a fixed end there's always a node. Okay? That's a rule. At a fixed end there's always a node. And you may also remember, just from watching this video here, that when the wave reflects at the other end, at the free end, as you're going to see in a second, it actually reflects in the exact same phase. So right about here, there is no node. There's actually the opposite of a node. There is an antinode. So one possibility is for the reflected waves to interfere with the incoming waves and form an antinode, the letter A, at the free end. So this is one possibility for a standing wave. It's actually part of a whole wave that we learned about when we did these the other day. Remember these that had nodes at both ends? This is kind of the same idea, just with one end free. What's another possibility? You could have a node at a fixed end. You could have an antinode at a free end. In between, you could have another antinode, and you could have another node, and things would look like this. Another possibility is to have a node at the free end, sorry, the fixed end, the antinode at the free end, and in between not just one node, but two nodes. Of course, in between every node is an antinode. So what would this one look like? It would look like this. Sorry, my drawing is a little sloppy. But you'd get something like this. And these are actually, maybe you are kind of guessing what these are called. This is the first harmonic. This is the second harmonic. And this one is the third harmonic. How many wavelengths do you see here? Maybe it'll help if we start down here. Let's count wavelengths. A full wavelength is when you see a full wave go up, down, down, up. So that's a full wave, but there's a little bit more. How much is this extra little bit here? Well, it's half of a loop. In fact, this over here is half of a loop. If you remember from the previous video, when you have 1/2 of a loop, and if you remember that a loop is a half a wavelength, well, that gives you a quarter of a wavelength. So getting back down here, here's a quarter wavelength, half of a loop, and here's a full wavelength for a grand total of 1¼ wavelengths. Or if you prefer to work in improper fractions, 5/4 of a wavelength. Of course, up here is a quarter wavelength. What do we have here? Here's a full loop, half a wavelength, and then half a loop, a quarter wavelength. This one is 3/4 of a wavelength. And so do you see the pattern? First harmonic, second harmonic, third harmonic. 1 node, 2 nodes, 3 nodes. 1/4 wavelength, now 3/4 wavelength, now 5/4 wavelength, so it's going up in odd numbers of wavelengths, odd quarter numbers of wavelengths. Okay? Now let's take a look at waves that are standing waves formed by reflection at 2 free ends. Well, the same rules apply. At a free end, you have an antinode, and of course, in between every antinode, every 2 antinodes, there has to be a node. So this one would actually look something like this. And the second harmonic, antinodes, we had 1 node there, now we're going to have 2 nodes. Of course, in between nodes, you have to have an antinode. So let's draw this. Here is the pattern for the second harmonic. Oops. Okay, and finally, the third harmonic. I had 1 node, 2 nodes, now I'm going to have 3 nodes. And antinodes in the middle. So let's see if I can do this. There we go. Once again, first harmonic, second harmonic, third harmonic. Let's look at the number of wavelengths we have here. Here we've got half of a loop, that's a quarter wave. Here's a half a loop, that's another quarter waves. 2/4 gives me half of a wavelength. Here I've got the same situation with a quarter and a quarter, but in here is a full loop for a half. This gives me, let's see, 1/4 and 1/2 and 1/4 again, right? That's a grand total of 1 wavelength. Or, if you prefer, I'm going to write it as 2/2 of a wavelength, and you'll see why in a second. Over here, here's a full wave. For once, I can just see a full wave, but there's also these 2 ends, which we know are quarter wave, quarter wave. So this is 1½ wavelengths, or if you prefer, 3/2 of a wavelength. And now let's look at the pattern. First harmonic, second harmonic, third harmonic. 1 loop, 2 loops, 3 loops. Half a wave, 2/2 of a wave, 3/2 of a wave. The pattern continues. And these are the standing waves that get formed when you have 1 or 2 free ends. All right? So now, to finish up, let's look at an application, how you would actually solve a question involving this concept. Remember that when we don't normally deal with standing waves that are free at 1 or 2 ends unless we're dealing with what are called air columns, those musical instruments that I pointed out to you at the beginning. So just getting back here, remember with a guitar string, you can have standing waves with 2 fixed ends. When do you have free ends? Not in a string instrument. A string instrument with a free end wouldn't work very well. That would be like a guitar with a string that's broken. Where you get these is when you deal with sound waves in a musical instrument, which are also known as air columns, a wind instrument. And in this case, even though we're dealing with compressions and rarefactions, we still draw them as if they are transverse waves because they're easier to see. Okay? So going back here, let's take a look at one of the questions. It says there's a sound wave with a wavelength of 120 centimeters. So they're telling you the wavelength here. So that's why I call the title of this slide Wavelength Constant. They said 120 centimeters was the wavelength. So I'm just going to write that down. It's given information. It says, standing waves are set up in an air column closed at one end. That means it's free at the other end. So immediately I'm going to start thinking about these kinds of waves because they're closed at one end, open at the other. So remember these ones. They're the 1/4, 3/4, and 5/4 wavelength waves. It asks you, what are the first three resonant lengths? What they're asking here is for an air column, such as, let's say, a clarinet. How long does the air column have to be to allow standing waves of the first, second, and third harmonic to exist? In other words, where would the musician have to close off or open certain keys on the body of the instrument in order to support these standing waves? So the way you do these ones is you need to imagine three separate lengths of air column. And in your book, you're going to see that they use kind of rectangular shaped representations of an air column. They're actually meant to be tubes, like cylinders, like a clarinet would be, but in 2 dimensions they look rectangular. And what you can do is, let's see, the first 3 resonant lengths, well, guess what? I happen to have drawn the first 3. First, second, and third harmonic is what that means. So we're just going to try to fit those waves into these air columns, and let's see how well I can do. I know there's got to be an antinode, whoops, pardon me there. There's got to be, if we imagine this to be the open end, by the way, and if we imagine these to be the closed end, just like this, okay, then what would we be dealing with? Well, at an open end, you have to have an antinode, yes. And at a closed end, you got to have a node. So one possibility is the first harmonic like this. Now the wavelength is 120 centimeters, so that means the distance, if I draw a full wave from the starting point to the next starting point is 120 centimeters. This is what they're telling me for any of these waves, which means that from here to here is half that distance, at 60 centimeters. And therefore, from here to here would be 30 centimeters. So right away you can see, oh, this is a quarter wave, 1/4 wavelength. We know the wavelength is 120 centimeters, so the length of this air column is 1/4 of 120 centimeters, and that's just 30 centimeters. That's the length of this air column. Now, suppose you want to go to a longer length, same wave, but in a larger air column. Now what would you have to do? Well, you'd have to go to a different harmonic because the wavelength, the distance, is still going to be the same from this node to that antinode. In this case, we're now going to have, I'm not drawing these to scale, by the way, so I hope, if any, whoops, that was awful. I'm not drawing these to scale. So, geez, not doing a very good job drawing here, am I? Okay, good enough. There's a bit of a time lag between what I draw and what comes up on the screen because I'm recording here and I'm using a lot of the memory of the computer. Kind of throws me off a bit. But anyway, here we have 3/4 of a wave. And so if we do a calculation in here, we have 3/4 of 120 centimeters. This is telling me, that comes to 90 centimeters, by the way. We need an air column 90 centimeters long in order to accommodate this wave. And I'm going to leave it to you guys to finish up with the next harmonic. Which one would you draw here? I think you can see the pattern. 1 node, first harmonic, quarter wavelength. 2 nodes, second harmonic, 3/4 wavelength. What are you going to draw here? I got to leave you with some of the work to do on your own. This is how you do this kind of question where the wavelength is constant, but it's the air column length that is variable. All right. Now we'll move on to one more. By the way, this question is obviously section 8.3, the review questions. I believe this is in your homework, either in class or after class. So there's a little bit of a jump on that one. In the same group of homework questions is another one. This time they say the air column is open at both ends. Okay, so right away I know that I'm dealing with these patterns, these standing waves. And it also says that the air column is 60 centimeters, but this time the wavelength is variable. And they ask for the fundamental, the first overtone, and the fifth harmonic. They're still asking for 3 wavelengths. However, this time the air column length is the same. So I'm going to draw myself 3 air column lengths, which are all the same. And what I'm going to try to do is imagine different wavelengths fitting in there. Now, how can different wavelengths fit in there? They can only fit in there if they are different harmonics. So with a 60 centimeter air column length, sorry, let me just put that in here. Oops. "60 centimeters from top to bottom." And remember, free at both ends, meaning what? Meaning I'm going to have an antinode at both ends with a potentially 1 or more nodes in the middle. Could be more than 1, it depends on the mode. The fundamental mode, remember that? That's a fancy word for the first harmonic. The first overtone, that's a fancy word for the second harmonic. You can look these up in your reading. Okay? And of course, the fifth harmonic is self-explanatory. So in part A, what are we going to have here? We want the first harmonic, antinode, antinode. So all we need is 1 node in the middle. So I'm going to draw this. Something like that. I see right away that this is a half of a wave, as we discussed way back over here, right? Half a wavelength. And if I know that half a wave is occupying 60 centimeters, I can write this. Half a wave takes up 60 centimeters, therefore a full wave takes up, you guessed it, 120 centimeters. That's the wavelength of the fundamental mode if I force it to be, if I force it to set up in this type of air column. Next up, the first overtone. So second harmonic, going to go in here. Well, the second harmonic has 2 nodes instead of just 1, and it looks a little bit like this. Okay, right here, you're right, it's 2 halves of a wavelength, setting itself up in an air column 60 centimeters long. Is actually a very easy equation to solve. 2 halves is 1. You actually have the answer right off the bat without having to use your calculator. This wavelength is different. And as before, I'm going to leave it to you to solve for the fifth harmonic. And that's how you do these, folks. You got to understand what the different patterns look like. You have to understand when you might want to use 1 fixed end, 1 free end, or 2 free ends. And of course, with string instruments like a guitar, 2 fixed ends. And you got to be able to notice whether it's the wavelength that's constant and the air column length changing, or is it the air column length constant and the wavelength changing. Okay? Anyway, I think we've covered everything, and as you heard from the bell, it's the start of another class. So thanks for watching. I will see you guys in class. Take care now.